Okay, so yeah, welcome to this second session on random matrix theory, and we'll be talking about the chapter 4 of the book, which was about Wishart matrices and the Marchenko-Pastur distribution. So it's another fairly basic or important random matrix distribution, and with Wishart matrix, the Wishart ensemble is like the matrix ensemble, and the Marchenko-Pastur distribution is the bulk distribution for the eigenvalues. And these are so this distribution actually has more is quite useful in practice because like Wishart matrices are like the distribution of sample covariance matrices for um, Gaussian sample for Gaussian variables. So they come up all over the place in like Bayesian modeling and so on. So the basic setup here is that we have t observations of n variables, and we call them xit. And these could be, for example, a time series from stocks, from neurons, or just observation of the same entity that you're measuring. And the key parameter of interest here is going to be this ratio n over t, which is going to determine a lot about what we get out of on one hand the spectral distribution, but also it's common to like when you have this kind of data, you want to estimate the covariance matrix. And for that, there's like a sample covariance matrix, like an estimator, a statistical estimator of it. And depending on this ratio, what you'll get out of it is going to be different. So we'll name Q as n over t, and we'll keep this parameter throughout. And really, there's two cases. One is Q is smaller than one, so when we have way more samples t than variables. And intuitively, that should be the best case, right? We have more than enough data to sample the covariance matrix. And the reverse would be when Q is greater than 1, when we have more variables than samples. And this is also quite a common case, especially, for example, in genetic studies. Like people, like your sample is like a person that you're analyzing the DNA, and your variables would be like whether some gene, excuse me, whether some gene is expressed or not, and you have like thousands and thousands of genes. So it's easy in this kind of genetic studies to have like tens of thousands of variables, but only a few observations. And so a common problem in this case to estimate the true covariance, the matrix of the data, or at least the eigenvalues and so on. So from now on, we'll be assuming that our xit are zero mean. Otherwise, as is standard in statistics, we can always just remove the mean, so that's not a problem. And as mentioned, we have an estimator of the covariance matrix called the sample covariance matrix. And if we assume, I think, yeah, if we assume that our xit, I put them in like a matrix with each column is an observation and call it H, that's going to be so my matrix of observations, and I take my sample covariance matrix as 1 over t times this product H times H transpose, which is equivalent to saying that the ijth element of E is simply 1 over t times the covariance of the variable I and variable j. And so this E matrix is in some sense the covariance of the variables, but we could also take like the transpose of it. Take F is equal to 1 over n here, H transpose H, and that would be similarly the covariance of the observations. And clearly these two matrices are related. In particular, they'll have essentially the same eigenvalues up to this like t or n factor, and so it's easy to see that t times E and n times F have the same eigenvalues. And moreover, if we say that, for example, Q is smaller than 1, so the case where we have more observations and variables, F will have n non-zero eigenvalues that are basically the same as the ones from E, so 1 over Q for the scaling times the eigenvalues, and then all the other eigenvalues t minus n are going to be 0. And the nice thing that this gives us a nice exact relation between the Stieltjes transform. Um, if you don't remember what the Stieltjes transform is, uh, the definition is over there, but we'll see a little bit more of it later. But the Stieltjes transform is one of the main ways we can like find out what the spectral distribution of a matrix distribution. And so we have like a nice relation between the Stieltjes transform of the F covariance matrix and the E covariance matrix. But generally we'll be talking about the E one for now. Okay, so because this is like a matrix distribution, we'll start by computing the moments. And so one, we have to remember that if the columns of H are drawn independently from a Gaussian with some true covariance C, then we know that the expectation of this product here is Cij times the Dirac delta of T and S. And so this means that when we take E to be 1 over T H transpose, so a Wishart matrix, that's how we define our distribution, right? It's a covariance matrix of a Gaussian distribution. Then one is easy to see that the expectation of Eij, if we unroll it, it's the expectation of this sum, and so we have this product here, and we can apply this formula, and we get 1 over T times the sum of T terms times Cij, and so it's equal to Cij. And so what this tells us that the expectation of the matrix E, so notice that here we have the expectation of the matrix, so it's a matrix. It gives us C, the sample covariance matrix. This is a bit maybe unusual because last time we said that for spectral distribution we were more interested into the expected the trace. So this one at the bottom would, instead of taking the expectation of the matrix, we would take the expectation of the trace of the matrix. So 1 over n. This can go on the other side, but right, usually we would be using these kinds of objects because they tell us directly about the spectral distribution. But in this case, it's nice that we can just show that the sample covariance matrix in expectation is equal to the covariance matrix, the true covariance. And so that means in statistical terms that it's an unbiased estimator of the true covariance. But unfortunately, it also has quite a lot of variance in some cases. So we can compute the second moment, so T of E squared. And in this case, we'll be taking tau, so this tau here is the expectation of the trace, the normalized trace of this matrix. That's why you have 1 over n times t squared. So t squared comes from these two products here, and 1 over n comes from the fact that from this tau. So we have 1 over n times t squared times the expectation of the trace of H transpose, H transpose. Unroll it and you get a product of 4 Gaussians and all packed in a sum. And so to compute these terms here, we use a result called Wick's theorem, which is about computing expectations of products of Gaussians like this, zero mean Gaussians. I refer you to the book if you want more details, but basically it's a formula to split up this sum and compute each term separately. But at the end, what we get is first the expectation of the second moment, so essentially the second moment of the covariance matrix, the true one, plus n over t, so that will become q times the same, and plus 1 over t times the same. And so in the limit as t and n go to infinity, assuming that their ratio stays constant, this term will go to 0, and so we were left with the tau of c squared plus q times tau of c squared. So, sorry, the square is outside of the parentheses here. So, yeah. So maybe one thing to comment here is that we see that essentially the variance of this sample covariance matrix is slightly larger than the variance of the true covariance matrix. And so we have this term that gets added that depends on Q, and see as Q, if Q goes to 0, so we get more and more observations and keep the same amount of variables, this becomes negligible. But if it doesn't go to 0, then we have a larger variance than just the in some sense the true variance of the covariance matrix. Even though I'm not exactly certain that it makes sense to talk about the variance of the true covariance matrix. But anyway, this is a physicist book, so we'll let that slide. Okay, so a few more things. So we can express the law, so the probability of these Wishart matrices. First, we need to, like, because we have this H that was a matrix of all independent Gaussians, so we can take express the probability of that as simply the product of all these Gaussians. And so this, for example, is for a single column J. I think for just a single column J. So we have all of these essentially these terms that essentially are a product of Gaussians, and so we have an exponential of this thing here. And then if we take the property of a single matrix H, that simply becomes, with some work, so we have again this term here with the determinant of C1, and there's an exponent T divided by 2 that gets bolted on. And then the exponential here, we get the trace of H transpose C inverse H. And with some like algebraic trickery, we can rewrite this trace as the trace of E times C minus 1. Essentially, we're using properties of the trace for that. Now, there's a big gap between these two steps. Essentially, if you read the book, they say, okay, we do the transform H to E, and then we compute like, there's a rule for whenever you're doing these kind of transform that you need to compute the Jacobian of this transform, and they have a whole paragraph on how to compute this paragraph. But anyway, the end result is that the probability of observing a single covariance, empirical covariance matrix E is looking like this. So we have on the right, or not on the right, on the left, we have this term T over 2 to the power of n T over 2 divided by a multivariate gamma function times the determinant of E to some power over the determinant of C times the exponential of minus T over 2 and times the trace of E to the times the inverse of C. Now, okay, this is all well and good. If you squint a little bit and if you've seen some advanced statistics, this will look like a gamma distribution. And in fact, if you take n, so just one single variable, this in fact becomes just a standard gamma distribution. So we have the probability of E is of the form b to the power of a times the gamma function divided as a. This is just a normalizing factor, so it's not super important, times x to the a minus 1 to the times e to the minus bx. So really you have to only need to remember that the gamma distribution is like a family of distribution of this form where you have a monomial times an exponential, and then the rest is just normalizing. What this tells us about it is that the Wishart ensemble in some sense is a generalization of the gamma distribution for Gaussian matrices. And in particular, so the gamma distribution in just univariate is very important in statistics because it comes up in a whole bunch of different applications, but most notably in Bayesian statistics. When you do Bayesian statistics with a Gaussian distribution, you'll have priors on the parameters of this normal, and a typical prior is to take the gamma distribution for the inverse of the variance. And so that's one way where the gamma, or in some sense, it means that, well, because we were studying these Wishart matrices as like describing the sample covariance matrices of Gaussian variables, and so sort of makes sense that it joins up with the univariate case. So yeah, in particular, you can use the Wishart distribution as a prior for this kind of stuff. Okay, so as always, feel free to interrupt to ask questions, especially since this one may be probably fairly short. We'll see. So we'll take a look at one special case of Wishart matrices, which is called white Wishart matrices, and that's basically the case where we take the covariance matrix to be simply O1, so the identity, and that means we have like a nice, sorry, yeah, a nice Gaussian distribution that just goes like it's anisotropic with the term, or there's no preferred direction, it's not squashed in any direction. So yeah, to just have to remember one trick is that the determinant of A, sorry, the determinant of a matrix E, so we can express it as the exponential of the trace of the logarithm of E. Notice that the logarithm of E here is the matrix logarithm, so it's a bit trickier than just taking the element-wise log. We have typically to, like, if you can write E as O lambda O prime, right? If you can diagonalize E, then log E would be, so the eigenvectors wouldn't change, but then you would apply the logarithm to the diagonal matrix lambda, and then the logarithm matrix logarithm of a diagonal matrix then is just the logarithm applied to each diagonal element. So that's how you would compute the logarithm of a matrix. So in this case, you need to compute an eigendecomposition, so it's very expensive. But anyway, if we use this little formula and we use that to like take this determinant term here and break it back into the exponential, we get something in the form that's just a normalizing constant times the exponential of minus t over 2 times this trace of e to the times the inverse of c plus a term depending on the trace of the logarithm of e. And then we just take c to be the identity matrix to get the something like this. So right, we get rid of the inverse term here. And so in the end, we get the probability of a white Wishart matrix, and we'll call them W, is essentially proportional to the exponential of minus n over 2 times the trace of some function v of W. And this is important because it means that the white Wishart matrices are rotationally invariant. And we discussed about that last time, that rotationally invariant matrix random matrices have this nice property that their eigenvectors are boring in the sense that they're uniformly distributed. And so this v function here, it's called the potential, and it has the form 1 minus 1 over q times the log of w plus 1 over qw. And generally, this white Wishart case will be studying it closer for the spectral distribution because it's easier to work with. All right, so let's get on to the actual spectral distribution. So the spectral distribution of the white case or white matrices is called the Marchenko-Pastur distribution. And we'll be just deriving it in the same way that it was that the spectral distribution of the Wigner matrices was derived last time, by using the Shor complements formula to express this. So we take one or matrix of independent normal standard Gaussians, H, set W to be 1 over T times H transpose. And then we construct the Steelers transform. So we take some Z, a complex number that's not in the spectrum of our matrix W, set M to be Zi minus W, and then we look at the trace of, so the Steelers transform will be the trace of, uh, yeah, sorry, so G of Z here is the complement, and then the Steelers transform is the trace of this matrix. I don't need to write this. So yeah, the standard construction here is just to set all this up and then use Shor's complement formula where you express the first element, so 1 over g of z, so the first element of the inverse of this matrix, so here it's equal to m. So 1 over this element is equal to m11 minus m12 times the inverse of m22 times m21, where these like m things are taking the matrix M and like cutting it into blocks. So we'll take M11 to be just 1 element, so a scalar. M22 will be a n minus 1 times n minus 1 block. And we'll use that to get a nice recursive relation going on. And then we have these like row and column vectors on that stick around. So applying this formula, we get simply like taking M11 is z minus W11. And then this whole thing here boils down to minus 1 over t squared times a sum over the t and s, so the observations, times a sum over the variables other than the first one. And then we get this nasty expression. So the book is a bit unclear on all the steps here, and I didn't get time to exactly like get what they were doing, but they were saying that this part here, this part included, we can like show that it converges to a like nice limit. And so in the limit of t and n growing such that the n over t is constant and some other properties or some other conditions, this essentially becomes so z minus w11, so that's the same, minus 1 over t times just a sum over the j and k things. And we have first a sum of over t, hkt, hjt over t. And actually this is equal to the wkj times the m22 minus inverse jk. And notice that we have somehow made these terms here disappear. I'm not entirely sure why, but that's fine. Plus some term of the order of 1 over the square root of t, so this will be going to 0 as we go to infinity. And similarly, this w11, it's equal to 1 plus some fluctuations, as they say in the book, on the order of the 1 over the square root of t. So again, this will be disappearing. So what this ends up giving us is that we have 1 over g of z equal to z minus 1 minus 1 over t times the trace of w2, and w2 is the I think w2 is like the 2 block. So like if m is zi minus w, then w2 is like this block minus the zi part. So we get the trace of a product of w2 times the Stiller's transform of this block here, so m22 inverse, and so plus some like fluctuations term, and so we can rework this trace term as, so we expand the definition of the Stiller's transform, or the not the Stiller's transform, the complement, the resolvent, excuse me. So yeah, we work this and it becomes minus the trace of I. So because I here is going to be an n minus 1 times n minus 1 matrix, it is going to be simply n minus 1 plus z times the trace of g2 of z. And so because this g2 of z is just the resolvent of a Wishart matrix of size n minus 1 times n minus 1, if we take n and t to go to infinity, and assuming that we're in the region where things work out, we get an equation at the limits where 1 over g of z evaluated 1, 1, or the first element, is equal to z minus 1 plus q minus qz g of z, plus again some fluctuations that will disappear as n goes to infinity. And so we end up, and again, this also tells us that this term here, 1 over g, has like negligible fluctuations, right? This is deterministic, and this would be the variation, and we can see the variation goes to 0. So that means that at the limit, we can take this term and take the expectation of, so yeah, the expectation of 1 over gz. That's going to be 1 over the expectation which is going to be 1 over g of z. So this last term, this last step is just the definition of g of z, but that's fine. And so we get, again, just an equation for the Stieltjes transform of a Wishart matrix, which is, again, a polynomial equation, so we have to find solution for it. So that should be on the next slide. Whoop. So the solution of this equation on the previous slide is in general form this. So we get g of z is equal z plus q minus 1 plus or minus this square root term divided by 2qz. And so once again, we have multiple solutions and we have to pick the right one that's going to be consistent with the what we know and should have for the rest for the yeah for the case that we're working with. And so through some work, so again, all this thing is just some complex analysis. So if you haven't done any of it, don't worry. I have some nice visualizations of what this function looks like. But the correct function ends up looking like this. So z minus 1 over q minus, we have to take the minus branch, and then like this product here is just the same as the above, divided by 2qz. Note that these lambda plus and lambda minus here, they're just the roots of this equation. So I think it's lambda plus or minus is equal, so 1 plus or minus the square root of q squared. So that's the roots of this equation. And so this is the Stieltjes transform, and we can actually take a look at it. So yeah, again, I have like a Pluto notebook for the Stieltjes transform. So this is for the case where q is equal to 1. So notice that you can view the matrix, and it's, well, not the matrix, the Stieltjes transform, and mostly it's going to have a peak and go to infinity at 0. I think, oop, yeah, no, that's not the case for q is equal to 1, but q is equal to 1.6. Yeah. And if we look at the corresponding imaginary part, so the way, let's go back to the slides. So the standard step is that once you have the Stieltjes transform, you can get the eigenvalue density as taking 1 over pi times the limit as you approach the real axis from below. So you take g about the x minus eta, where eta is some positive number. And this ends up looking like the square root of lambda plus minus x times x minus lambda minus over 2 pi qx. So essentially this part here just disappears. And then there's another term that gets stacked on, because remember, if we have n greater than 2, not greater than 2, greater than t, we have some 0 eigenvalues that should also be here. And so this is what this term accounts here for. It's a delta that basically represents a peak for the zeros of our spectrum. And so if we go back to the visualization, right, so this is the imaginary part of this function, right? So this is a complex function, so it has a real and imaginary part, and here I'm just plotting the absolute value. And on the bottom, I'm plotting just the the imaginary part. And so the idea is that we approach the real axis from below. So if you imagine the horizontal line as approaching the function from below, we get close and close, and then here it blows up. That's because of the software, but normally if we pick, yeah, so that's the density. Let me pick a Q that will behave better for this. So let's pick Q, yeah, smaller than 1. So here we should be in a good situation. So again, oop, okay, if we wait a little bit, let's pick a bit lower. Unfortunately, it has to compute everything. Okay, no, that's good. So yeah, if we pick a Q that's lower than 1, we get something like this. So just a peak at 0 and then something a bit wonky on the rest. Yeah, interesting. I think you can see, unless that's the, so you can see that there's a bit of a like a cliff here. So that's because the support goes to 0. So if we look at just the imaginary part, so let's get closer. So this is the imaginary part of this function. If we get closer and closer to from it on the right here, eventually we get to 0. And if I approach it just the right way, we get something that essentially is the spectral density of the Wishart matrix. And it's interesting to look at it from the other side. You can see that it looks like a cliff, but really it's like a cut in the function. And so if we approach from the other side, it goes to the negative. So that's why we have to approach it from the other side. But generally, this curve here is the density. Yeah, and you can see it here. So that's the general form of the Marchenko-Pasture density. So we have like a peak, not quite at 0, but a bit before, and then a sharp drop. And then not pictured here if Q was greater than 0, not greater than 0, Q greater than 1, we'd also have a peak at 0 for this. Let's try that again. Yeah, so here the imaginary part is a bit not super happy about this peak, so it's not super accurate. Especially around 0, it should be different, but here it's not great. So, but the distribution looks like this, so it's more spread out. But then there should be a peak at 0 that's indicating that we have like these by default 0 eigenvalues. Okay, so I think that might be enough visualization for today. So yeah, that's the spectral distribution of this matrix. Remember also that, okay, the function here, this function here is the like bulk density, but the eigenvalues themselves, they're not sampled independently. So even though they only follow distribution, there'll still be some spacing between them because they're not independent from each other. So yeah, so that was white Wishart matrices. For general Wishart matrices, it's a bit more difficult, but the general idea is that if you imagine a general matrix sample covariance matrix for a Gaussian sample with just a covariance matrix C, which is arbitrary, the way to go about this is to first take the diagonalization of C, so where lambda is the eigenvalues and O is the orthogonal matrix of eigenvectors. Then we can write the square root of C as simply taking the same idea of the log, right? We apply the square root to each element of the diagonal matrix. And then to generate a sample from this distribution, First, we generate X from a white Gaussian. So basically, we're sampling each element from a standard Gaussian, and then setting Y is equal to C square root times X. And we can see indeed that, for example, the expectation of Y times Y transpose, that becomes this, and the X times X transpose has expectation 1 I, so this simply becomes C, the covariance matrix. And similarly, if we do the same construction for our H matrices, right, to construct this sample covariance matrix, we get something that looks like this. So the sample covariance matrix here is equal to 1 over t times the square root of c times H transpose, and H is supposed to be like standard Gaussian, so the white case again, times c square root. And so we once again have a sandwich of the square root of c and a white Gaussian, so a white Wishart matrix. And note that this kind of product here it's called a free product, and that's a term from the field of free probability, which is more physics, but you can imagine it as the probabilities of non-commutative variables. And that's like a whole can of beans. But the rough idea is that if you want to do probabilities on things that don't commute, for example, matrices, right? The product of matrices is not commutative, and you want to do probability with it, you have to sort of extend probability in some way, and so that's free probability. And in general, like to get the spectral density and so on of like just an arbitrary matrix ensemble, we'll need to use free probability, but that's much later in the book. So yeah, that was it for today. Any questions? So yeah, why do we care about the eigenvalue densities? So it's a good question. So in the case of like Wishart matrices, you might care about it because if you use Wishart matrices to model, like to do Bayesian learning for matrices, then knowing what distribution of eigenvalues you should get means one, you can compare the actual values you observe to what you should expect and tell, okay, this is not follow distribution. It's also interesting if you imagine a problem where, say, it's easy, for example, in dynamic systems, to have a situation where you have, so say, for example, a system that follows around some equilibrium, right? So how to make this clear without using too much dynamical systems. Like imagine some kind of like a bridge. A bridge can be stable or not. So if it's stable, it's like the bridge will sort of not, will not explode if you sneeze at it. It will, like, if you deform it a little bit, it'll go back to like its nice stable state. But if it's unstable and you move it, you tip it a little bit, it might break all of a sudden. And so this idea of looking at the stability of a system around some state, usually you do that by looking at a linearization and you get a matrix. And whether the system is stable or not depends on the eigenvalues. And so now if you assume that you have a system that has some like randomness in it, then you need to use the tools of random matrix theory to tell you, okay, here's the distribution of the eigenvalues of a matrix, and then I can know, okay, if they are within this range, I know that my system is stable, and I'm fine. And then if there's non-zero probability that some eigenvalues in the unstable range, then I know that I might have some issues. But that might be being a slightly too involved example. I don't know. yeah, maybe more closer to home for machine learning. Um, like a lot of the application of RMT to machine learning has been looking at the spectral distribution of trained models and using that to say, okay, if I look at this distribution, this tells me whether my model is trained or not. And you can also, it's in the same way that people look like at the distribution of activations or the distribution of the weight, usually the distribution of the eigenvalues will be more interesting. But in this case, you just like the empirical one. Yeah, so livelihood cares a lot about it. So yeah, sometimes I want to set priors on eigenvalues to anchor certain properties. For instance, I want to predict elections for the House, Senate, and presidency. Then I predict the first principal component, yeah, which would roughly correspond to the variance. Yeah, will have much larger eigenvalue than the other. Okay, that's an interesting example. Thanks. Okay, any other questions? I guess not. So yeah, that's. I think we can leave it at that. So thanks everyone for coming.